Greetings, Panthers. Dr. Augustine, and we are going to take a look at the next step along this titration curve. We've already looked at the first point of the titration curve. We've looked at region 2, the buffer region. Remember, we need the Henderson-Hasselbalch equation to solve any titration in this region from initial 0 just beyond 0. So the first drop of sodium hydroxide that's added all the way up to just below the equivalence point. And so the last video had how to solve those two regions. So here's our example problem. Calculate the pH during the titration of 40 mils of a 0.1 molar propanoic acid. HPR is the shorthand for it. We have a Ka value after each of the following additions of 0.1 molar sodium hydroxide. So we did 0 milliliters. Remember, that's just a rehash of the last chapter. We also did 30 milliliters. If you have not watched the prior video, I recommend you do that before you try tackling this one. This video is going to say what happens when we're at the equivalence point, which is 40 milliliters. And again, just a reminder, if you're just looking at this for the first time, this picture is not for this titration. This picture is a generic weak acid, strong base reaction. And so 40 milliliters does not mean like right here on the curve. This just means this is kind of the shape of the curve. Our particular case here with these molarities and these volumes, the equivalence point is going to be at 40 milliliters. So this is at the equivalence point and then beyond the equivalence point. How do we deal with this point right here? And how do we deal with all the points beyond the equivalence point? All right, we are going to start with the exact same table that we had in the last video. This is a mole table. This is not an ice table. Number of moles initial, number of moles change, number of moles final. We'll start filling it out right now. So I've already written down the conditions, 40 milliliters of a 0.1 molar propanoic acid and 40 milliliters of a 0.1 molar sodium hydroxide. All right, so this is going to be 4.000 times 10 to the minus 3 moles of propanoic acid and also 4.000 times 10 to the minus 3 moles of hydroxide. And we've got 0 moles initial of the propanate ion. Now, you notice there's a 1-to-1 ratio, and it's 1 mole, 1 mole. They have the exact correct number of moles. So what that means is this is going to go down by 4.000 times 10 to the minus 3 moles. They're in the exact stoichiometric ratio, minus 4.00 times 10 to the minus 3 moles. And then, of course, because this is in a 1-to-1 ratio, and so is this, for every one of these that goes down, one of these gets produced. So I'm going to have 4.000 times 10 to the minus 3 moles changing plus that amount on the product side. So the number of moles final is going to be 0 for propanoic acid, 0 for hydroxide, and 4.000 times 10 to the minus 3 moles of the conjugate base of our starting acid. Okay, so here's a time to stop and think about what's happening. So now we have a solution that's only made up of water plus conjugate base. So because this is water and conjugate base, they're actually in equilibrium with one another. So we have a reaction that looks something like this. The conjugate base plus water yields conjugate acid plus OH minus. And if you recognize, if you look at this problem, we are going to need some kind of an ice table here to figure out what the concentration of OH minus is going to be. And so what we're actually shooting for is to find the POH. Remember, that's equal to minus the log of the OH minus concentration. If you look at this problem, you look at so think about what we got, what's happening here. We've got water and conjugate base together in solution. There's no hydroxide and there's no propanoic acid anymore. All we have is the conjugate base, the propionate, and we also have water. So now we've got a situation where that is going to be in equilibrium, forming the conjugate acid, the propanoic acid, and hydroxide ions. Now, because we don't have an H3O+, we can use this POH expression to find out what the concentration is. So this is another ice table. This is a chapter 16 type problem. So at the equivalence point, we're going to use the information that we have the number of moles, and we can set up an ice table to figure out what this concentration is going to be. Here's where it gets a little bit tricky. That is moles, not molarity, right? We need molarity here to fill into the ice table. So our next step is going to be to figure out what is this concentration of the conjugate base. And so that's going to be equal to the number of moles of the conjugate base divided by V total, I'm going to call it, which is the new volume in my solution. So think about this. You started with 40 milliliters of the propanoic acid, but you have now added 40 milliliters of base to it. So this V total is actually the sum of those two volumes. So I'm going to need to consider the number of moles, which we found above, 4 times 10 to the minus 3 moles PR minus, divided by 0.0800 liters. It's 80 milliliters. I'm calculating this in my head. And so that's 0.5000 molar. That's the concentration of my solution. So that is going to be my initial concentration. And I have 0 of this, 0 of this. This is going to go down by x. This is going to go up by x. And now we're going to have 0.0500 minus x plus x plus x. And we are going to get a KB expression now. Got to be a little bit careful. This is the base that we're talking about now. So that's going to equal to concentration of HPR times concentration of OH minus divided by the concentration, the original concentration of the propionate ion. And that whole thing is going to be equal to x squared over 0.05000 minus x. That's going to equal to KB. So at this point, you might be asking yourself, how do we find KB? That wasn't in the problem. Well, if you remember, Ka times Kb is equal to Kw. So we can find, if you know one of them, if you know the Ka or if you know the Kb, you can always find the other one through this expression. So we're going to solve for Kb. So Kb is equal to Kw divided by Ka, which is going to equal to 1.0 times 10 to the minus 14 divided by 1.3 times 10 to the minus 5. So that is going to equal to 7.7 times 10 to the minus 10. That is the value for Kb. All right, so we're going to write this all in one expression. Kb is equal to 7.7 times 10 to the minus 10. That's equal to x squared over 0.05000 minus x. And I'm guessing you have done enough of these problems to recognize 10 to the minus 10 is much, much smaller than 10 to the minus 2, which is what that is, 1, 2. So since it's such a huge difference, we can make our favorite approximation. 7.7 times 10 to the minus 10 is approximately equal to x squared over 0.0500. And then we are going to solve for x. I'm going to skip some steps. I'll let you do these on or convince yourself this is right. 6.2 times 10 to the minus 6. And if you recall, x, 6.2 times 10 to the minus 6, remember the OH minus final concentration is the value for x. So that is also equal to the concentration of OH minus. All right, how does this help us? Well, once we have the OH minus concentration, we can plug that into POH here. And we know that the pH plus the POH is equal to 14.00, or in other words, pH is going to equal to 14.00 minus POH. All right, so all we need to do is find the POH, then we can find the pH of the equivalence point, 14.00. So we need to say POH is equal to negative log of 6.2 times 10 to the minus 6. And that actually equals to 5.21. That's the POH. So 14 minus 5.21 is equal to 8.79. That is my pH at the equivalence point for this reaction. All right, so a couple things to notice about this. We noticed we were at the equivalence point. We had the exact same number of moles of acid and base, so they both zeroed each other out. That's the stoichiometric point, the equivalence point. But you notice the pH doesn't equal to 7 at this case. The pH is actually a little more than 7. It's a little basic. Does it make sense that it's basic? It should, because the only thing left is a conjugate base. Because we have conjugate base left in solution, we anticipate that the pH is actually going to be more basic than if we have a strong acid, strong base case. So when we titrate a weak acid and a strong base, the equivalence point has a pH higher than 7, and that's because what's left over, after this reaction's done, what's left over is conjugate base. And the conjugate base then goes into equilibrium and it forms OH minus, so we end up with a basic solution. So one thing to be aware of, when you have a neutralization reaction, it does not automatically mean that the pH is going to equal to 7. It depends on what's actually being titrated. So if we have a weak acid and a strong base, we're going to end up with a pH above 7. If we have a strong acid and a weak base, we're going to end up with a pH less than 7. Okay, the last step we're going to tackle here. What happens when we get past the equivalence point? This 50 milliliters represents something beyond the equivalence point. And what's going on in this region is we're now past this point, and we're into this region where we've gotten past the equivalence point. This is now excess OH minus. So it's another limiting reagent problem, and we're going to use POH from the concentration of that excess OH minus. So here's the setup. Once again, we have a mole table. This is not a molarity table. We have a mole table. And if you want to, you can stop the video now and fill out this mole table based on this information: 40 milliliters of a 0.1 molar HPR, 50 milliliters of 0.1 molar NaOH. Fill this guy out, stop the video, start it up again, and see if you end up with the right numbers. All right, so we return to the table, and we've got the same starting number of propanoic acid. We've got a little bit more sodium hydroxide now, so we've got 5 times 10 to the minus 3. Of course, we start with zeros of these. This one's going to run out first. This is the limiting reagent, the propanoic acid, so that's going to go down by 4 times 10 to the minus 3. We're going to end up with 0 propanoic acid. That's going to go down by 4 times 10 to the minus 3. It's in a 1-to-1 ratio. So we're going to end up with 1 times 10 to the minus 3 of hydroxide, and we're going to end up with 4 times 10 to the minus 3 of the conjugate base. Now, at this point, OH minus is a strong base. That is not a strong base. So we can actually ignore the contribution from the propanate. This is where all the action is. The hydroxide is where all the change in the pH is going to happen. So in order to find the POH, we need the concentration of OH minus. And the concentration of OH minus is going to be that number of moles of OH minus that we just found, 10 to the minus 3, divided by the new volume, which is going to be 0.04 plus 0.05, in other words, 90 milliliters. And the new concentration is going to be equal to 0.01111 molar. There are 4 significant figures on this problem. So the POH is going to equal to 1.95, and the pH is going to equal to 14.00 minus 1.95, and that's going to equal to 12.05 is the pH of this solution at 50 milliliters. In theory, now you should be able to calculate every single volume along here, and you should be able to create a theoretical curve for a weak acid strong base case. Just to make sure you understand the ideas I've been presenting here, here's the same curve for a weak base and a strong acid. And you notice it basically looks the same, it's just inverted. Okay, we have an initial point here. Let's say we're using ammonia, so it'd be 0.1 molar ammonia. So you could find the pH of that 0.1 molar ammonia. What information would you need in order to do that? You'd need to know the Kb value for ammonia, right? So we could find the pH of that. We end up with a buffer region. The buffer has ammonia and the ammonium ion, which is the conjugate base or conjugate acid of the buffer. We'd have a certain equivalence point pH. Notice the pH is less than 7, as we mentioned, and then this is the excess OH minus. So you should be able to, at this point, do any of these problems, either strong base, weak acid, or strong acid, weak base. They're basically the same problem. It's the same strategy. The only thing that's trickier about this problem is here we're going to find POH. The buffer is going to find pH if you do it correctly. This is going to find pH directly, and then this is going to be excess H plus or H3O plus, and we can find that, we can find the pH from that directly. Whew, okay. That is a lot to deal with. This is a challenging set of problems because it's complicated, each different region. The last video in this series from section 17.4 is going to be some summary statements and some big picture stuff about how you pick indicators and all that sort of stuff. So this is the second to last video in section 17.4.